So,
Rose Studio and food.
let's get right to it. Do you remember?
And then we made stuff. It's
We
good.
get the lights down.
It's really cheap actually. It's like $20.
We used to have a setting that was darker.
Is this going in the garage?
There, is that better? You just have to push harder. Okay.
It's like $20.
You remember last day we crushed this 55-gallon drum, and to demonstrate the atmospheric pressure that we live in day after day, which is in this country 14.7 pounds per square inch. But we found that here in Provo, where we're way up high in the mountains, it's really only 12.4 pounds per square inch. But there's a lot of square inches on that 55-gallon drum, and so that was a huge force. But of course, the 55-gallon drum doesn't just naturally crush like that. We had to remove the air from the inside so that it was only the pressure from the outside acting on the drum. There wasn't anything inside pushing out. Now, today I want to demonstrate that same atmospheric pressure with this ping pong cannon. And it's a really simple device. It's just a PVC tube, open at both ends initially, and I'm going to put a ping pong ball in there, and then I'm going to seal off the end with a piece of mylar. This is just the material that they make party balloons out of. It's really thin, but it's strong, and so I'm going to put this ping pong ball in there, and then I'm going to cover this end with the mylar, and then I'm going to there we go. Okay. And then I'm going to do the same thing at the other end. And I already did that before class started. I put a piece of mylar down there. And then what I'm going to do is I'm going to pump all the air out of this tube, and then with this nail, I'm going to puncture the mylar at this end. Now that's going to cause air to rush in from this side with atmospheric pressure. We've got nothing in here because of the pump, and that's going to send that ping pong ball. We've got a little stand to hold a Sprite can, and this device is there so that the pieces of the Sprite can don't go here. Okay, so this is protection, and so what am I missing? No, I think it's good. I think it's good. Now, I want to point out that this atmospheric pressure is going to get that ping pong ball going at more than 500 miles an hour, 70% the speed of sound. Okay, and we'll learn all about sound next semester. Let me pump that down. You can do it. You can do it. Now, this is going to be loud, so if you want to preserve your ears so that you're not damaged like I am, you can just... Okay, let's do this.
No.
I'll do it on 3. 1, 2. Okay.
Yeah, not a fun.
I thought it was good.
Not bad. Okay. Now, I call this the ping pong cannon of death, and that's because at the end of class, I'm going to get rid of this, and I'm going to stand up here, and it's hit this target here, okay? And I put that at the end of class because I really want you to learn about Pascal and Bernoulli. And I'm not sure how this is going to go. Okay, with your clicker real quick, we all know the answer. We learned this last day. On which of those blocks of wood is the buoyant force going to be larger? And these blocks have the same volume, and they're, now let me get you started here. Okay, now you can click.
Oh wait.
Okay.
It does smell.
Last call, get your vote in. Okay, remember the rule. If everyone gets it right, I take you all to Disney World. Let's see what happened. Oh, I'm sorry. We're not going. That's too sad. Okay. Now, remember why that is, okay? You remember that Archimedes taught us that the buoyant force, that force upward by the fluid, is always, whether it sinks or whether it floats, equal to the weight of the fluid that's displaced, pushed out of the way by the object. Now, in the case of this block on the left, it is displacing more liquid. The part that's underneath the surface is displacing liquid, and this one is displacing less. And so by Archimedes' principle, the buoyant force would be greatest on that block. Now, if something floats, remember the 10-ton ship, if it free floats, there's only two forces on it. There's a weight force down and a buoyant force up. And if it's just floating there, it has zero acceleration. So the diagram has to string balance. And that means by Newton's second law, remember you've got to qualify that, with zero acceleration, the weight of this block has to be greater than the weight of that block. Indeed, this weight has to equal that buoyant force, and this weight equals that buoyant force. Now, given that those two blocks have the same volume, but not the same mass, they have different densities. So one might be oak, a high-density wood, and the other might be balsa with a small-density wood. Yes? If they had different volumes, you can see that if I made this piece of balsa big as a ship, it would still float high, but the buoyant force would be greater because there'd be a whole bunch of balsa underneath the liquid. Okay? Okay, what should I remember? We just went through that. Archimedes' principle always applies. That's in your toolbox. First and foremost, whether it floats or whether it sinks, the buoyant force is always equal to the weight of the liquid displaced. So that's what you go after. You try to figure out how much weight of liquid got pushed out of the way. And then if it floats, that's a big if right there, okay? This tool in your toolbox only comes out of the toolbox if it's floating. The buoyant force is also equal to the object's weight. Again, a 10-ton ship has to displace 10 tons of liquid in order to float. Okay? Check on your neighbor. See if your neighbor is still on the bus. Okay. Last day, I made a claim, but we didn't have time to support that claim. I said if you can only see 10% of an iceberg, that means you can't see 90% of it. And if you can't see 90% of it, that means the density of the ice is 90% the density of the water. Okay? Well, let's see if we can show that's true. I've got a simple problem here. A cube of wood that is 20 centimeters on each side, placed in a tub of water, and we find that it floats so that 6 centimeters of the block is above the water and 14 centimeters is below. Okay? So we're going to try to figure out the density of that wood. Now, if what I told you is true, and you shouldn't believe me, you know, you don't trust old people just because they're old. If what I said is true, we would expect, since 70% of this block is under the water, we would expect its density to be 70% the density of water. Tell your neighbor real quick, what's the density of water? 1. In MKS unit. Oh, that's different. Really quick, MKS units, what would it be? Yeah, 1,000 kilograms per meter cube, okay? So 70% of that would be 700 kilograms per meter cube. Well, let's see if that's what we get. If we draw a free body diagram for that block, we have the weight force down and we have the buoyant force up, okay? Now, we know that it's not going anywhere, so it has 0 acceleration. And the weight force we've dealt with a long time. It's just mass times gravitational field strength, 9.8 newtons for each kilogram. Okay? Now, this is where we're going a little bit different than we've been before. I can write that mass as the density of the wood times the volume of the wood. Why is that? Well, density is how many grams I have in 1 unit of volume. And volume is how many units I've got of volume. So that's going to give me the total mass of that block of wood. Now, if I look at the buoyant force, that's equal to the weight of the water in the Casper box. Let's remember, what's a Casper box? The Casper box is that Casper the Friendly Ghost. It holds stuff, but it doesn't have any mass of its own. And the Casper box is the same size and shape as the liquid that's displaced. And so that's going to be the Casper box right there, the part that's underneath the surface. Now, again, that's just the mass of the water in that Casper box times G. And then I can do the same trick I did up here. The mass of the water is going to be the density of the water, that's the 1,000 kilograms per meter cube, times the volume of my Casper box. Well, that's what we get. Now, with Newton's second law with 0 acceleration, those have to balance each other. And so when I substitute in, this is what the weight is, this is what the buoyant force is, I can get rid of G. And now, remember what we're looking for. We're looking for the density of the block. This is what we want right there. So this is math, this is algebra. I just got to get rid of that volume of the block by dividing both sides. And now, lo and behold, what I get is the density of the block is equal to the density of water times this ratio. The volume of the Casper box, the part submerged, divided by the total volume of the block. Since the Casper box makes up 70% of the total volume of the block, I'm going to get 70% of the density of water. And that's the answer that we were expecting, if Greg was telling the truth. If Greg was telling the truth. Talk to your neighbor and see if your neighbor followed that little derivation there. If not, slap them.
The top one of the entire box, the box is open support that's submerged.
Okay. Questions?
So the entire bomb was headed into
You would not need to reproduce that derivation on any exam. I just wanted you to see that I was telling you the truth. Right at the end of class, we had this hard problem. You're floating in a boat in your own pool because you're rich. And I gotta tell you, pools were just not a thing in Montana. I mean, it was winter 10 months of the year, so that just was not a thing. But anyway, you live somewhere where there is a pool. You've got 6 gold bricks sitting in the floor of the boat. Again, you're rich. You reach over with a marker and you mark the level of the water on the side of the pool. And then, one by one, you throw those bricks of gold over the side to the bottom of the pool. And the question is, does the water level in the pool go above that mark that you drew on the side? Does it go below, or does it stay right at that mark? You voted on this last day. We didn't do so good. We didn't do so good at all. Let's do it again. You can click. Remember, last day I told you that stays the same is not the right answer, but I didn't tell you what the right answer was. Okay. Last call. Get your vote in. Okay, folks. I just said stays the same. That's right. But at least no one voted E. Okay. Let's talk about it. There's your pool. The water's a little yellow. I don't think you're using enough chlorine. There's your boat, and we're just going to use 1 brick of gold. Let's not complicate this, okay? Now, when that brick of gold is floating, how much water does it displace? These are your choices. Does it displace an amount of water equal to its volume or equal to its weight? Tell your neighbor real quick. Volume or weight? Okay, let's shout out our answer. 1, 2, 3. Weight. Okay, weight. Okay. When something floats, it displaces an amount of liquid equal to its weight. And when you're looking in your homework in some of the problems, they ask you, like in problem 5, what's the mass of that clay ball that you put in those 3 beakers? Well, you look for an experiment where the clay ball floats. That's the one that's going to tell you about the mass and hence the weight. Okay. Now it turns out because lead bricks have these are gold bricks actually. I've never had one actually. They have such a high density that it's going to take a whole lot of water to weigh the same as that brick of gold. Okay? That's displacing a whole lot of water. How does it do it? By making that boat ride very low in the water, pushing water out of the way. Now, if I throw it over the side to the bottom of the pool, now how much water is being displaced by that brick of gold? Equal to its volume or its weight? Shout it out. Volume. Volume. Where the brick is now, at the bottom of that pool, water used to be, and it had to go elsewhere. And so you see, I'm displacing a whole lot more water when it is in the boat. You see this boat is riding higher than it was here, and so that means the water level goes down. Down. Okay. Now folks, you are fortunate that I have been teaching a long time. Because when I started out teaching, That's a question I put on my exam my first year at Montana State University. And I was just, you know, I didn't know. And the average on the exam was 40%. Okay. Over time, I've learned that there's some questions that are better used for teaching than for exams. Okay, so that's, you're welcome. Other questions on that? Yes? Yeah. Well, if something is totally submerged, where it is now, water used to be and had to go somewhere else. Okay. This brick of gold is still displacing an amount of liquid equal to the volume of the liquid displaced, but now a lot of water is being displaced by the boat riding really low. And so if I drew a free body diagram here, I would see that it's the weight of the brick of gold that's going to tell me how much water is displaced. Okay. Suppose you were meeting a friend at an outdoor cafe in the summertime, and you get there before your friend, and the waiter brings you a glass of ice water with a single ice cube sticking up out the top, and he's filled up that glass all the way to the brim, all the way to the brim. Now you don't want to start without your friend, so you just sit there and wait patiently. You're probably reading your phone, okay? And as you wait for your friend, it's a hot day, and that ice cube melts until it's completely melted. Now, while you were waiting for your friend, did the water in that glass spill out, go down, or stay right at the brim? Talk to your neighbor. Talk to your neighbor. Up and over, goes down, stays the same. Okay, we just saw those that read the book. Okay, in the book we have the same problem as an example, but it's disguised. It looks a little differently. What we did in the book was we started with a great big bucket, and we filled that bucket up to the brim with water. And then we took an ice cube. But this is no ordinary ice cube. This is a Mondo ice cube. This is 5 pounds. That's American units, okay? 5 pounds of ice, okay? And when we lower that carefully into that bucket of water, water gets displaced. Well, because it started out full, displaced means spilled onto the table, okay? Now, the question is, how much water spilled? Well, usually the answer is a free body diagram. If I look at the free body diagram for the ice cube, the block of ice, if you will, I've got, well, the weight is 5 pounds. That's why we call it a 5-pound block of ice. Okay? Now, the other force is the buoyant force, and that's equal to the weight of the water displaced, or in this case, spilled. And so that means since there's no acceleration, that spilled water has to be 5 pounds of water. Now, suppose that I pick up that block of ice. I've got gloves on, so I'm not going to get frostbite. And I just hold that block of ice above the bucket, and I let it melt. Drip, 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 drip. How many pounds of water do you figure I can get out of 5 pounds of ice? 5 pounds, yeah. And so that's going to fill that up to the brim. Okay? And so that's essentially, Thomas?
Sorry, I kind of want to challenge this concept a little bit.
What's that?
I want to challenge this concept a little bit because our ice cube has more surface area than water does, right? That's what I'm
More volume, you mean?
Right, but it's the same weight. And so if it's going to condense when it melts to become smaller, how's it going to
Well, let's answer Thomas's question by turning this whole experiment around. Suppose instead I started with the empty bucket and I glued the ice to the bottom of the bucket. And then I filled the bucket up to the brim. And then I let the ice melt down there at the bottom. What's going to happen to the level of the water in the bucket? It's going to go down because, remember, ice has a smaller density than water. So as the ice cube melts, it takes up less space. Now, in our case, the ice cube wasn't displacing its whole volume when we started. Half of it was above the water, half was below. And so as it melted, it took up less space. Turns out just the right amount of space to keep that water level. That answers the question for you? Thank you. Okay. Folks, the most famous example of buoyancy in the scriptures is this one here. Okay. And I just want to point out something that I did not realize for many, many years. I had always thought that this scripture indicated Peter's lack of faith, Peter's failure. Peter just didn't get it done. And then my dear friend and the co-author of your book, Ron Helling, when I was serving as a counselor to him in a YSA bishopric, I remember him teaching the young people, Peter was the second best water walker in the history of all time. Okay, he was the second best of all of them. And so we should not see this as Peter's failure, but dang, he did okay. Okay. Let's take a field trip here. We're going to go to a pond, a primordial pond, and we're going to have the pressure of 1 atmosphere at the top of that pond. And if we go down, remember we learned this last day, if we go down 10.3 meters in fresh water, what we do is we change that 1 atmosphere to 2 atmospheres. We increase the pressure by 1 atmosphere. Now, this particular pond has a little kind of, do you call that a nook or is that a cranny? I forget. Anyway, it has this little pocket of water over here. And the question is, what would I expect for the pressure at that point? Would I expect 2 atmospheres, bigger than 2 atmospheres, or less than 2 atmospheres? Talk to your neighbor about that. What would I expect? Okay. Here's another way to think about my question that I asked you. If I were to take a drill with a really long drill bit and drill a hole parallel, horizontal, through that rock, once I get the hole finished and it fills up with water, is the water going to stream to the right through the hole or to the left through the hole or just stay put? What do you think? Yeah, it's just going to stay put. Okay? And so that means that the pressure over here is also 2 atmospheres. 2 atmospheres. Okay? Now, on a particular day, it happened to be a Friday, we had this asteroid come screaming down, and that sent a shock wave that immediately sent the pressure at the top of the pond to 5 atmospheres. The monkey's dead, okay? The monkey's gone. Gone. Okay? The question is, what pressure do I have down there 10.3 meters below? Is it 6 atmospheres or 10 atmospheres? Talk to your neighbor. 6 atmospheres or 10 atmospheres? Okay. I hope that each and every one of you reached into your toolbox and pulled out that very important tool. And you see, what we are doing with that asteroid is we are adding 4 atmospheres to this side of the equation, from 1 to 5. And you remember with algebra, we got to do the same thing to the left-hand side of that equal sign. So this is going to change the pressure at this point and at that point to 6 atmospheres instantly. Okay? Now, it turns out we don't need an asteroid to make this happen. All we need is a big enough giant with a big enough plunger, and that giant, if he or she is strong, can give us whatever pressure we need at the top. And that's going to be transmitted throughout the fluid to every part of that liquid. Now, the first person to teach us this was Severus Snape. No, this is Pascal. He's a mathematician. And he taught us that any change in pressure applied to an enclosed fluid is transmitted undiminished to all parts of the fluid and the enclosing wall. Now, this was a big deal up in Montana, and that's because a whole lot of my students came from farms and ranches, and they knew how to work. They really knew how to work, and that's why we call it Varric in physics. But a lot of them had big, huge farm equipment that ran on hydraulics, okay? And so this is the principle behind hydraulics. Now, I need 2 volunteers, and let me see, who hasn't volunteered lately? Okay, you haven't volunteered yet, have you? Okay, do I have a football player? Yes, come on now. No, come on now. What's your name, sir?
Who's up your last one? They're off Tuesday.
Oh, wait, no, that way, Logan.
Katie, but close.
What's that? It's not even close. Okay, I'm calling you Logan. Haley, okay. Haley and Logan, people. Okay, Haley, if I could have you over here. Actually, yes. What we have here, folks, are 2 syringes that are partially filled with liquid. And are you right-handed? Right-handed? Okay. Left-handed people are more likely to become scientists. They're also more likely to go to prison. So those of you that are left-handed, choose, okay? Choose today. With their one right thumb, when I say go, they're going to try to push their plunger all the way in so that the other person's plunger is pushed out. And so it's essentially, we're going to call this a new Olympic event, dueling syringes. And so, get ready, get your thumb on the syringe, and don't go until I say, ready, set, go. Oh, Logan, she's beating you. Oh, yes, Haley's the winner. You have come to realize that sometimes these things are just rigged by the universe. Okay, so I'm going to turn these around and give Haley the large diameter syringe, and we'll do this over again. Ready, set, go. Oh, he beat you bad. Okay. Let's give him another hand, please. the person with the fat syringe has no chance. No chance at all. And that's because of this, we call it Pascal's principle. Okay? For a tie, if this was all on a horizontal plane, for a tie, we would want the pressure at this point 1 to equal the pressure at that point 2. That feel right? Okay? Now, remember, pressure is force divided by area. The force being the force that Haley is putting on this plunger, okay, divided by the area of the plunger. Well, for a tie, because let's say that Logan, that's not his real name, but we're going to call him Logan, let's say that his area is 4 times bigger than Haley's area. Well, that means for a tie, he's got to provide, with his thumb, 4 times the force. And that's just not likely. Okay, does that make sense? Speak to your soul. Okay, this is what explains hydraulic equipment, like a car jack, a car lift. Okay, if I've got a car that weighs 2,000 pounds, but I can't lift 2,000 pounds, what I would do is set up a system where I've got a large cylinder and a small cylinder and 2 different plungers. And if I fill that with some liquid, water's going to rust things, so it'd be some sort of oil. What I find is that if these are at the same level, then for a tie, well, they would have the same pressure. And that means that if I put a little force on this one, I get a big force up over here. So let's say that the ratio between this area and that area is 10. The big one's 10 times bigger. That means to lift a 2,000-pound car, I would only need to push with 200 pounds. Does that seem like I'm getting something for nothing? I put in 200, I get 2,000. That's just like the stock market some days, but not all. Okay? So what gives? We know that's not free. What do we have to do to pay for that magnification? In the back, sir, say it loud.
The 200 has to be applied for a longer amount of time.
Perfect, perfect. If I want to raise this plunger by 1 inch, I got to fill up the area underneath the plunger with oil. That means I got to move enough oil out of this little cylinder to fill up that 1 inch over here. So I got to push this down 10 inches. My little force times 10 inches is equal to my big force times 1 inch. Force times distance, what does that remind you of? Werk, yeah. So the werk in is equal to the werk out.
Wrong.
But if what you want is to magnify your force, you're willing to pay that price of pushing for a bigger distance to get the bigger force. Now, in practice, you would want this point to be lower so that the pressure down there would be greater than the pressure up there. Okay? That's Pascal's principle. And on a final exam, any question about that is going to be conceptual, okay? Fairly straightforward and conceptual. Let's change gears here. We've got stick Picard and stick Spock on the side of a road, and this road goes down from 4 lanes to 1 lane. And each of them has a clicker, a counter, kind of like the greeter at Walmart, okay? And every time a car goes by, they click, okay? Now at the end of the day, at the end of 24 hours, who's got the bigger number of clicks on their clicker? Tell your neighbor real quick. Okay, hope you see that if they get different numbers on their clicker, we've either beamed down cars from the Enterprise or we've beamed cars up to the Enterprise. Okay? Whatever path is Picard has to pass Spock. But because I've only got one lane over here, they're going slow, waiting for their turn to get going, and they're going fast here. You've all been in this traffic jam, right? And once you look and see what's causing the disturbance, zoom, you're out of there. Now, there won't be any questions about cars and pipes. We're going to do fluids in pipes, okay? And so instead of cars, let's replace that with a fluid. And this is a chunky fluid. Those of you from New Jersey know what I'm talking about, okay? Now, I'm going to concentrate on one chunk of that fluid, that chunk right there. Now that chunk was going slow, it's about to go fast. Well, that means that it's accelerating, it's speeding up, okay? Now, how's that going to happen? Well, it's going to happen if I have a big pressure behind it and a smaller pressure in front of it, so that the net pressure on that chunk is going to be to the right. Check that your neighbor followed that argument. Do a buddy check. Okay. Now, what we notice is that where the velocity of the liquid, the fluid rather, remember a fluid can be either a liquid or a gas, where the velocity of the fluid is small, the pressure is big, and where the velocity is big, the pressure is small. Now, Daniel Bernoulli, also a mathematician, was able to actually put this into a formula, Bernoulli's equation, and it looks similar to things that we've seen before. 1/2 rho, remember rho is mass per volume, times v squared. That's looking like a kinetic energy per unit volume, okay? And this is for a fluid that's all going through a horizontal pipe, so that there's no change in elevation. If there was change in elevation, there would be another term in this equation that looks a whole lot like gravitational potential energy, rho GH. So we're going to stay away from those problems in 105. If you want to deal with those problems, take Physics 123. Okay? Now, we don't know, and we don't care what that constant is for any given liquid. We just know that it has to add up to the same thing at every point in that liquid, or fluid rather. And so that means that whenever I have a large pressure, I have a small velocity, and vice versa. Small pressure, large velocity. Now, an example of that would be a stationary truck with a tarp that is stretched over the top. And if you stretch it tight, it's fairly flat there. It might sag a little bit due to its weight. But if you get that truck going down the road, well, it bulges up. Why? Because above that tarp, I've got a big velocity, the air streaming by. Inside, I've just got potatoes, very little or no velocity. And so I get a big pressure inside compared to the pressure outside. I had a very humiliating, embarrassing demonstration of that. My wife and I bought this beautiful dining room table set at Costco with 8 chairs, beautiful chairs, big old heavy chairs, monster chairs. And so I got a friend with a truck to help me take that home from Costco. And so we went there and we loaded the chairs into the truck on top of the table that was flat on the bottom. And And we decided not to tie them down because they were really heavy. They weren't going anywhere. They weren't going anywhere. Well, my friend got going down the freeway, and the next thing I know, these chairs just pop up and then down onto the freeway, and there's just pieces of chairs everywhere. Now, why am I telling you this? Because you can't do this in Utah, but in Montana there's only a car coming by every 10 minutes. And so we could pick up the pieces of those chairs and take them back to Costco. And that's a walk of shame, okay? And so I walked in and I said, my chair's broke, and I'd like to buy some more chairs. I said, oh no, we'll replace them. And Costco's wonderful. They put brand new chairs in the back of our truck, and we strapped them down. Okay, let's demonstrate this. Let's start with this blower. Okay. Now, I've got a stream of air with high velocity. And remember, air is a fluid, okay? So a high velocity is going to have low pressure compared to the rest of the room where I have no velocity and high pressure. And so that means that if I put something in the stream, it wants to stay in the stream. When it tries to get out, the high pressure outside of the stream pushes it back into the low pressure in the stream. Let's see if I can get this spinning. Yeah. Wingardium Leviosa. Okay. Now, let's try something else. A little more awkward. Oh, sorry. Good catch. Okay, I'm going to be on the soccer team. Now, I have some high pressure air here. And if this is just a bottle that's cut out of the bottom. There's a splash zone here, okay? You might want to move any electronics that you don't want wet. When I put the stream of air over the top of this, it's got a little straw through the top. When I force the air to go fast across that top, that causes a low pressure area. And that's going to cause the high pressure, atmospheric pressure, outside of this what do we call that again? I lost my word. Yeah, bottle. It's gonna, the high pressure outside is going to push the water up. Okay? You didn't even have to pay extra for that. Now, we can do that same thing with the high pressure, or the low pressure, high velocity. When it's spinning, I can be a dentist. I've got a drill. Now if I turn that down, let's see if we can. Okay. Not bad. Not bad. what I'm going to do is turn this around. Let's do it so you can see it. Okay, I think I should move that. Okay. Now, and again, I'm required by the university attorneys the following announcement: do not try this at home. I am a professional. Let me not go on the microphone. Okay. Thank you. Okay, so we're going to replace the mylar here. It's got a hole in it, of course. Okay, and then over here, we're going to, and of course, the ping pong ball is no longer there. Saw that coming. And so I'm going to put the ping pong ball in, put the mylar over the end, and then I'm going to track the mylar. Now, clearly, I can't do this alone. I'm down at that end. I need someone that's willing to send a ping pong ball at 500 miles an hour into my body. Anyone here willing to do that? Come on down, sir. Okay, let's give him a hand. Okay, so let's make it so that it points towards me. Okay, is it going to hit the target? Yes. All right. We have another prayer. I'll just say it. Okay. Give everyone a 1, 2, 3 count so that they can cover their ears, and then just poke it. Three, 2, 1. Now, my friends, I have a confession to make. I cheated. You probably didn't recognize me because I still have my disguise on. Okay, I have for your enjoyment 2 old exam questions. Now you remember last day I promised you that year after year, semester after semester, the problem that is missed more than any other on that exam is the buoyancy problem, okay? Even though you learned about sinking and floating in the 2nd grade, okay? They can be challenging. We're going to have things that are floating or sinking in heavy cream or alcohol or water or salt water. There's all sorts of ways we can dance these problems. So where are my helpers over here? I have 2 helpers on this side. You've all heard each other. Right here. I think I have this. I'm just going to pull it best. Another helper on this side, please. Okay. I'll get back.
I think I'm just going to it's just like, huh? It's like, where is it? The Pong thing, it's at the I'm saying you have to do the BPC with me. My friends that go, the care clinic, like the South Dakota. I was Spanish. Yeah, I know. I've been at the Molly. Huh? I've been doing the Molly one. But the Molly, it's up in Salt Lake. I don't know. Oh yeah, why didn't you? What is it? No, it's the Molly. It's just like, I think it's like the purple one. It's the same thing. It's just like the Salt Lake. But I'm like applying for the it takes a long time. It took me all summer. And this is how I met there. I mean, I just like put it down my head. So when I started, what I applied. I did start this, technically. Yeah, I started like at the beginning of the semester and it's taking all this time. You've been working since the beginning of the semester. Yeah, no. I've been doing like 5 hours a week there. It's just so chill, dude. Like you fill up and you're out by like 7. It's Tuesday and Thursday. Well, the translate. I do flood, so I'm there.
I'm a very lucky man because
what time do you start? I go like
okay.
I get like 5 hours.
Let's look at this big G problem. We are told that this big letter G has a volume of 400 centimeters cubed, and that it's fully submerged in water. Now, folks, let me just back up a moment. Some of you are still struggling with these buoyancy problems. At the YouTube channel, there is a review session that's an hour and 10 minutes, where I just start with simple buoyancy problems and then go to a little bit more complicated and then a little more than that, and just work our way up through different problems. And so if you know in your heart of hearts whether you're having a good time with this or it's challenging. If it's challenging, I would suggest that you go and watch that video and hit pause whenever you need to. I'll send out a link, if you can't find it, I'll send out a link as soon as class is over for you. In this case, we are holding this big G down under the water, completely submerging it. And these 2 strings that are holding it make an angle of, why wouldn't it be 53 degrees, right? It could have been 37, but those are the only 2 angles we know. Each of those strings has a tension of 1.5 Newton. And the density of water, of course, is 1 gram per cc. So the first thing we're asked to do is draw a free body diagram. And folks, free body diagrams are so second exam back in dynamics. But as I promised you, that section on dynamics was the foundation for everything that comes afterwards. When you get to 106, we're going to be doing dynamics, only with electric forces and magnetic forces. And whenever you're dealing with forces of any kind, the first step is always a free body diagram. Now, when you're in the testing center, you're not going to be able to write on your exam, so you need to bring scratch paper. And don't worry about wasting the scratch paper. Go ahead and waste it with your free body diagrams, because that's not a waste. That's the only way you're going to get the right answer. So draw yourself a free body diagram real quick. Okay, that should have been enough time. For every free body diagram, we start with the weight force, Earth on the G. That's just the mass of the G times G. Then we ask, are there any magnets in the problem? No, of course not. So, what touches that G? Well, we've got the water, and it creates, we can add all the force by the water, remember that's in that tutorial, into one upward force that we call the buoyant force. Okay? And that's by the water on the G. And then I have two strings that are pulling, and they're pulling with a tension force on the G of 1.5 newtons. Okay? I'm gonna repent of where I put that. Okay? Now, we want to find the magnitude of the buoyant force, and to find the magnitude of the buoyant force, that's always equal to the weight of the liquid, in this case water, displaced. Spell it right? With an L. Okay, I knew it didn't look right. Now, that means what I do is I take that big letter G, and I imagine that I have a duplicate of that G made of water. Okay? I tried. You know I can't draw. Now I know that the volume of that G is 400 cc's. Well, it's submerged, and so all 400 cc's are displacing water. So what I want to know is, how much does that much water weigh? Imagine in your head, use your imagination, taking that big G of water and putting it on a scale and finding out how many newtons that reads. Well, the way I can get from cc's to grams is through the density equation. The density of water is equal to the mass of water that's displaced divided by the volume of water displaced. Now, I feel silly writing that up there because the density is 1, and so it's just a 1-to-1 ratio. So 400 cc's is going to be the mass of the water displaced is going to be 400 grams. Everyone see that? Now I went through this step here because I could have made that heavy cream, and I could have said that the density of the cream was 1.5 grams per cc. And then, instead of 400 grams, it would be 600 grams. See if your neighbor followed that. See if they understood what went down there. We want water.
So that's the mass. The weight force.
Well, so I have displaced with that G 400 grams of water. So if I take 400 grams and multiply it by 9.8 or 10, that's going to be 4,000 newtons. Wrong or sick and wrong?
No, sick and wrong.
Sick and wrong. What do I got to do to those grams first? Convert them to kilograms. Because G is in newtons for each kilogram. And so I'm going to have to change this to 0.4 kilograms. And that means that this buoyant force is going to be 0.4 kilograms times 10 newtons for each kilogram, or 4 newtons. Okay? Now, if I take this force, let's look at the one on the right, and I know that that force is 1.5 newtons. I also know, let me write that over here, I also know that I can break that up into an x part and a y part, and that angle there is going to be 53 degrees because this angle here is 53 degrees. Now, this is a 3, 4, 5 triangle. 3 times something, 4 times something, 5 times something, and the something here is 0.3, okay, newtons. And so this is going to be 3 times 0.3 newtons, and this will be 4 times 0.3 newtons. So this is going to be 0.9 newtons, and this is going to be 1.2 newtons. See if your neighbor followed that. So we want to find the mass of the G. If I know the fact that this is just staying in place with 0 acceleration, that means all the force up has to balance all the force down. Okay, so essentially I just did F net in the y direction is equal to the mass times the acceleration in the y direction, and that's 0. So I've got 4 newtons up, that would be positive. I've got 1.2 newtons down from the left string. I've got 1.2 newtons down from the right string, and then I have the weight force of the G, and that's got to equal 0. And so that gives me the weight force of the G is going to be 1.6 newtons. Okay? So what we wanted was the mass of the G, not the weight of the G. And so I know that this is equal to the mass of the G times G, which is, we'll call it 10, 9.8, 10 newtons for each kilogram. And so that means that the mass is going to be 0.16 kilograms. And that's equal to 160 grams. Okay. Questions so far? Yes, sir.
So for the force of buoyancy, why do we times the 0.4 kilograms by 10 newtons?
Oh, because it's not the mass of the water displaced that gives me my force, it's the weight of the water displaced. So if I took 0.4 kilograms of water and asked how much would that weigh, I got to multiply by G. Okay? So, the mass of the big G is 160 grams, and now we want the density of the big G. Well, the density of the big G is going to be the mass of the big G divided by the volume of the big G. That's going to be 160 grams divided by, we were told that that was a volume of 400 centimeters cubed, and that's going to give me 0.4 grams per cc. Now, if we cut those strings, it's got a density less than that of water. What's it going to do? Yeah, it's going to float. It's going to float. And we want to find the acceleration of the G, and this is important, people, right after we cut the strings. Once that G starts moving, we got to worry about the friction forces we call viscosity. We're not going to deal with that. That's just messy. That's just ugly messy. And so before it starts moving, it still has an acceleration, otherwise it would just stay there, right? And so we want that acceleration right after we cut the strings. Well, that's really easy. Cutting the strings just means get rid of those forces on your free body diagram. And now I've got, we said that this was 1.6 newtons. I don't have that tension force anymore. I've got 4 newtons up, I've got 1.6 newtons down. I can find my acceleration. Anytime you want an acceleration, you want to pull that Newton's second law out of your toolbox. If I call up the positive direction, then I'm going to have 4 newtons up, that's positive. I've got 1.6 newtons down, that's negative. And that gives me my mass, we said was 0.16 kilograms times the acceleration. And I can solve that, and I get an acceleration of 15 meters per second squared up. Okay, I raced through that because we were out of time. People, I will post the solution to both of these problems after the afternoon class today at the website. Have a great weekend, folks. May the net force be with you.
You guys don't have a class on Tuesday, right?
I don't think so.
We don't?
I don't think so.
Someone told me we didn't, but I never saw it was confirmed. I mean, I probably wasn't getting anywhere.
Yeah. He sent out an email like